Hi guys, welcome back to physics. I hope you had a great long weekend, for whatever weekend means these days. This week we'll be covering potential energy. If kinetic energy from last week was the energy of movement, then potential energy is stored energy. It's like energy that has the potential to do something. You could think of it like um, energy that could be used. Could be is the operative word there. So you can move something, push something, heat it up, use electricity, something like that. But most importantly, potential energy is energy that's not being used yet. It's probably most proper to say that potential energy is due to the physical arrangement of two objects, or multiple objects, where they are relative to each other. So further away, things like that. You could also say it's due to the position, and this is the most technical, the position of an object relative to some energy field, like a gravitational field or an electrical field, something like that. Field theory is not something we want to really get into in Physics 1. That's a much more advanced idea, though. Probably the most common form of potential energy you interact with every day is gravity. Lifting things up gives them more gravitational potential. Dropping it releases that potential. Another common form of potential energy you encounter is electricity, like in batteries. We're only going to deal with two types of potential energy in this class, gravitational and elastic. There's two reasons for this. First of all, they have simple formulas we can deal with pretty easily with algebra. We don't need calculus. And secondly, I want to save other types like electrical potential energy for Physics 2 when we deal with those subjects more directly. So let's get to the equations. The potential energy equation we're going to be using by far the most is the gravitational potential energy equation. PE equals mgh. Mass, m, times the acceleration of gravity, g, times height, h. You might ask, height above what? And we'll get to what that really is in a bit. But for now, think about it as simply the height above the ground. Maybe you have like a ball and it's some height above the ground, h. This is actually an approximation for the real potential energy. It's only valid when the value of g, the acceleration of gravity, doesn't change that much. So as long as you're sticking close to the surface of a planet, that should be okay. For our purposes, I think the guideline is as long as you're inside of Earth's atmosphere, that's lower than 100 miles, say, above the surface of Earth, then this approximation is good enough and you should use it. If you feel like going to space, you'll need to use the full equation. Thankfully, we can derive that full equation from this approximation. It's not so hard. Since the approximation here we're making is the value of g, the acceleration of gravity, not changing, we're going to sub in the equation for gravity that does change. You might remember that actually from our unit on force and acceleration last semester. But if you don't, I'm going to write it down here for you. Little g, the acceleration of gravity, is equal to big G times m over r squared. Remember, the m is the mass of the planet, probably in our case, or really whatever object is doing the gravitating. The r is your distance from the center of that object or planet. And big G here is not the same as little g. It's the universal gravitational constant. So I guess there's another big assumption in this equation too, which is that it assumes that all masses, not just the planet, but all masses are point masses, which means that they don't have any size or shape. They're perfect geometrical points. For us, in gravity especially, this isn't a very big problem, since it turns out that as long as you're outside of the planet, meaning like not hovering somewhere in the mantle, which you might find difficult to do, as long as you're outside of it, the gravity from that planet does actually pretty much act like it is coming from just a point with all the mass concentrated at the middle. Looks pretty nice for us. So we're going to sub that g equation here back into the PE equation. So the gravitational PE is the little m first from here times, now we're going to sub this in, big G, and this is a big M, over r squared times h. I guess I'll put another dot there for multiplication. We need to simplify this a little bit. Let's go through piece by piece. It's important to note a couple of things. Big G is not little g. They are different. Big G here is not little g. Little g was the acceleration of gravity. On Earth, it's 9.81 meters per second squared. Big G is the universal gravitational constant, which is 6.67, roughly, times 10 to the negative 11 Newton meters squared per kilogram squared. And second, these are different m's, little m and big M. In our case, I'm treating the little m as like, well, say like it's this person hovering out above the planet. It's the person's mass. And the big M coming from this G equation is the mass of the planet. Okay. So this isn't so bad. We do need to deal with this H. I promised you I would. I said before that it's in the approximation, it's the height like above the ground, maybe. In reality, it's actually the height above or below any point you want. So really, if you have your ball and here's the ground, you could have it. Most of the time, it's useful to think about the height being from where the ball is to the ground. But maybe you want to catch the ball before it hits the ground. And in that case, it might be useful to think of this height as h. Or maybe you have some sort of scenario where you want to lift something up and you want to see how much potential energy it's going to gain. There's your ball again. And you want to lift it up to that height. The height above it could be the h. And you could get like a negative, since it's below, you can get a negative potential energy there. Really, you're measuring the potential energy in this approximation relative to some arbitrary point that you get to choose. It's not fixed. So you get to choose where your so-called 0 point is. And you can choose any 0 point that's, I guess, advantageous. So say, for example, maybe you're holding a rock out over a cliff. There you are. So legs are off to the side. But you're holding a rock out off of a cliff, and the ground is really like, I don't know, 20 meters below you, right? But there's like a little extra cliff shelf, maybe 5 meters down. It would be more advantageous for you to make this your h rather than going all the way to the ground and making that your h instead. Okay, so h is a relative term, and you get to choose where it's relative to. One of the tricks of these problems is choosing a relative h that is advantageous to what you're trying to do. When we're working with the non-approximation equation here, we actually don't want to. We want to be relative to some more absolute 0 point. So in the case of hovering above a planet, the 0 point of potential energy is actually right here at the center, where the radius is 0. And that actually tells us what h is. It's really, in this non-approximation case, the distance from the center of that object you're interested in this non-approximation. So an h actually, in reality, turns into an r. So this r here that we just got is going to cancel out with the squared. And I'm going to rearrange this equation a little bit to give us something that looks a little nicer. Here's the potential energy for gravity equation that is not an approximation. Big G, little m, big M over r. Just one r, not squared. So this equation, we're not going to use it too much. But if you want to be out in space, if you want to be doing things with really large objects very far away from each other, this is probably the one you want to use for gravitational potential energy. Again, as long as you're on Earth, we're probably going to be fine. In fact, I would say as long as you're on Earth, definitely use MGH. All right, last but not least, let's take a look at the elastic potential energy equation. This guy is useful for things like springs, rubber bands, really anything that's stretchy or compressible, but then snaps back to exactly its original size after you've let go of it. In Physics 2, we're going to come back to this idea, and we're going to see that it's actually derived from the spring force equation. We call it Hooke's law. And we typically try to have the first few days of Physics 2 be an experiment to figure out what that spring force equation is. And don't worry, it's very, very simple. You should look forward to it. If you have let's take a spring, stretched or compressed, a length x away from where it is by default. So let's say that this is its default length. If I stretch it further, this length here, the distance I want for x is actually the difference between where I've stretched to where it likes to hang out. So I'll call this x here. The distance where it likes to hang out is called equilibrium, by the way. So x is really the distance away from equilibrium. So it could be stretched. It actually also could be compressed, too. I guess you'd have to draw very tightly compacted here. So yeah, x could also be the distance it compressed away from equilibrium. Either direction. For rubber band, it's kind of hard to compress them. So that kind of elastic is just the stretching kind. But for springs, I think springs are a really good example because they both stretch and compress evenly. So if you have that length x away from where it is at equilibrium, and it has a stretchiness, this is called a spring constant, that actually, it's more related to the stiffness of the spring. We call that the variable k. The potential energy stored in the spring is given by this equation, PE is equal to 1/2 k, that's the sort of stretchiness, springiness constant, times x squared. It's important to note that k is unique for any individual spring. So you have two springs made of the same thing, but say, for example, they're coiled differently. They're going to have different k's. K is measured in newtons per meter. So yeah, here's our equation for the potential energy in a spring. 1/2 k, that spring constant, times x squared, the amount it's stretched or compressed away from equilibrium squared. And that gives us a potential energy. Just like any other energy, it's measured in joules as the unit. And it kind of looks like, I hope you'll notice, it kind of looks like the kinetic energy equation, 1/2 mv squared. They have very similar forms. You have the 1/2, you have some constant, in this case, the stretchiness of the spring, in the other case, the mass of the thing moving, and then something squared, the distance from equilibrium or the velocity. And there's a reason they look the same. It's actually because they come from not the same source, but they have the same math done to them. So for potential energy, and this, in fact, this is for any kind of potential energy, any kind of potential energy is equal to the integral. If you're not in calculus yet, don't worry about this. Potential energy is the integral of the force associated with that energy. For gravity, it's gravitational force. Yeah, just there. So any kind of potential energy. So for springs, it would be the spring force, which you'll find out what that is in Physics 2. If you're in calculus already, which I don't think very many of you are, you can just take a derivative of this PE and figure out what that equation is ahead of time. Oh, you'll be so much ahead of everyone. So exciting. For gravity, though, you can take an integral of the gravitational force and get the gravitational potential energy, which we've already seen. But for KE, it's the integral of momentum. So kinetic energy for an object is the integral of momentum with respect to velocity. So it's the same mathematical thing going on, which gives us the same sort of structure to the equation, but the things in them are very different. So K and M are not really analogous, nor are X and V. I guess X and V are closely related in some ways. So it's more of a mathematical similarity than it is an actual physical similarity. I know it's weird, but that's how physics works sometimes. Any type of potential energy can be converted into kinetic energy, and kinetic energy can be converted straight back into potential energy. There's a lot of ways to do this, and we'll go over those later. In the case of gravity, for example, you simply let the object fall, and as it falls, the amount of potential energy decreases because that height decreases above the ground, right? But it speeds up too, so the amount of kinetic energy increases. And it turns out that if you add the kinetic energy and potential energy together, that total amount, the sum of all the energy, doesn't change at all. That's the concept of conservation of energy, the idea that energy isn't created or destroyed, just converted into different forms. I like to think about it as you have a certain amount of water in two different buckets, and you pour from one into the other. But you don't lose drops because you're really careful. So we'll see more about that concept in our problem-solving video, which comes up next. You can find a link to that down below in the description. And yeah, have a great one.